Okay, so this is problem number 53, once again from chapter 15. Okay, so here's what's going on. There's a block B sitting on top of block P, which is attached to a spring, and it's oscillating with some frequency F. Okay, there is friction between the top block and the bottom block. There's no friction between P and the ground. Okay, and what's the question is, what is the largest amplitude with which this can oscillate such that so this guy is going to oscillate back and forth. It says what is the largest amplitude it can have such that the large block still sits on it. Okay, this problem is actually a very simple problem. We've already done problems like this where you have to find with what acceleration P can move such that B sits on it. Okay, now in order to achieve this, we'll use the simple fact that the that the acceleration is related to the motion, okay, or rather to acceleration is given as a function of time according to the relation negative a times omega square times cosine of omega t plus phi. Okay, this is something that we know. You could go back into your notes and take a look at it. Okay, since we know this, we know that the maximum acceleration you can have, okay, the magnitude of the maximum acceleration is going to be a times omega square. Okay, but now omega itself is equal to f equal to phi. No, actually it's the other way around. It is f equals omega divided by 2 pi. So omega is equal to 2 pi multiplied by f. Okay, so we can rewrite my A max as A times 4 pi square f square. Okay, so this is equal to 4 pi square A times f square. So this is the maximum acceleration you can have. Now, since the reason block B is sitting on the surface, okay, is because of the friction, the friction between block B and the surface. If the mass is m, then we know that the maximum force that is acting on block B, the greatest amount of force, greatest possible force, F max on B is equal to the maximum force of static friction, okay, which happens to be equal to mu s mg. As a result, the maximum acceleration of block B is equal to simply mu s times g. And this, we know, is equal to 4 pi square A times f square. So this gives us A equals mu s times g divided by 4 pi square f square. Okay, so this is the answer to problem number 53. Okay, so in this problem, this is problem number 69. What you have is, you have a large disk of radius r, and there's a little disk of radius lowercase r, okay, and the masses of the disks are okay, it's capital M and M. Okay, and in the beginning, what you have is a small disk making an angle theta with the vertical. It is released, and we need to figure out what the speed is at the bottom, and we have to show that the speed v is some expression, okay, which looks like rg times 1 minus cosine theta divided by m over m plus r over r square plus 2, and all this multiplied by 2 and to the power half. Okay, so we have to show all this. Okay, so as you've recognized that the problem is essentially very simple. It's one of mechanical energy conservation. We show that MEI equals MEF. That's what we're going to use. Now, if MEI equals MEF, what we know is that the the total initial energy is simply due to the fact that this disk of mass small m is making an angle theta, so it has some height. Okay, so the MEI is equal to m times g times r times 1 minus cosine of theta. Okay, because if we were to measure the height from the lowermost point, we would get the height difference to be what r times 1 minus cosine theta. So that's easy. On the other hand, at the bottom, the only kind of energy we have is the energy of due to rotational motion. Okay, r1 half I omega square. Now the problem is very simple. Okay, let's figure out the moment of inertia first for the entire system. And what we have is we have the moment of inertia for the disk, which happens to be 1 half m times r square, plus we have the moment of inertia for the smaller disk. The large disk is 1 half m r square. For the small disk, we're going to have to use the parallel axis theorem. Okay, so that is going to be equal to the moment of inertia of the disk itself, which happens to be 1 half times m times r square, plus it is going to be equal to m times r square. Okay, so now we have all the terms here, and we can substitute. We get mgr times 1 minus cosine of theta is equal to 1 half, okay, times I, which happens to be 1 half mr square plus 1 half lowercase mr square, lowercase m, actually, you know what, this should be lowercase r. Let's fix this. So this is lowercase r square plus m times capital R square. Great. Now times omega square. So now, omega square is equal to mgr. First we can multiply everything by 2. So let's, you know what, before we do that, let's do this. mgr times 1 minus cosine theta, okay, divided by, let's get rid of all the factors of 2 here, okay, so it will be 1 over 4 times mr square plus lowercase mr square lowercase m times r square plus twice m times capital R square. Great. Now the 4 will end up in here, and so my omega will be equal to twice, what can I do? I can rewrite it as 2, or rather omega square, let's write omega square first. It will be equal to 4 mgr times 1 minus cosine of theta divided by, okay, now let's divide the denominator by, or let's factor an m times r square out of the denominator, the lowercase m times r square. Okay, so we have m times capital R square, and now what I'll have to do is I'll have to divide the first term by m times capital R square, the second one by m times capital R square, and all I'm going to be left with is 2 for the last term. Okay, so now this becomes 4 mgr times 1 minus cosine theta. Okay, you know what? The m's cancel out. There is 4g, and there is no r now, so it will be 4g, and then there is an r in the denominator, and what I'm left with is m over n plus r over r square plus 2. Okay, so this gives me my omega. So my omega is square root of all this, so it becomes 2 times square root of g times 1 minus cosine of theta times r times m over m plus r over r square plus 2. Now it's asking for speed, and speed v is equal to r times omega, so it becomes 2, and when I take the r here, the denominator r and the root gets cancelled. There's one extra r that's left, so I gr times 1 minus cosine theta divided by m over m plus r over r the whole square plus 2, which is exactly the expression that we wanted in the beginning. Okay, so this gives us the speed. Now the second part of the question is finding the time period, and we want to show that the time period of motion is 2 pi times m plus 2m times r square plus m times r square divided by 2 mgr to the power half. Okay, so that is our goal. Now, to achieve this, we're going to go back to the basic problem itself. And what we have is the reason, and this is for time period for small oscillations. Okay, so we're going to take theta here. Okay, and what's happening is that the force of gravity on this little disk, which will be mg, is what is responsible for the torque. Okay, so at any angle theta, what we know is that the torque on the system is equal to negative mg times r times sine of theta, which is torque. Okay, and this is equal to I times alpha, which is equal to I times d2 theta by dt2. Now, for theta small, okay, we know that sine of theta is approximately equal to theta. So I can rewrite this as I d2 theta by dt2 is equal to negative mg, negative mgr times theta. Okay, and so this now tells me that d2 theta by dt2 is equal to minus mgr divided by I, and I, if you recall, is equal to 1/2 mr square plus 1/2 m times lowercase r square plus m times capital R square. So this is all my I, and all this is multiplied by theta. Now this, you see, is nothing but the equation for a simple harmonic oscillator, with omega being equal to square root of mgr, okay, divided by, now you see I can once again get rid of all the factors of half, so I'll move that half up, and I'll have capital mr square plus lowercase mr square plus 2 times m times r square. And once I get this, my time period is simply 2 pi over omega, which is equal to 2 pi times mr square plus m lowercase r square plus twice mr square divided by 2 mg r. Okay, and that is essentially what we wanted to prove. Right, so this is problem number 69 from the textbook.